Right, where we left off... Whoops, what's going on? Oh, where we left off yesterday was... Yeah, we learned a lot about different syntax within functions. We learned especially about the where thing. Yeah, where we can add something. And we can do that with let as well. We can add a value, a function, helper functions, whatever. To our functions. Yeah, we can add functions to our functions and all that stuff. We learned about patterns and guards, right? Function, you build it like a pattern. Oh, this... Love the original song. This was just... Let's just take something else random. Yeah, it goes through them one by one, the patterns. And within the patterns, you have the guards where you can do more comparative stuff. Yeah, greater than, less than, and stuff like that. Well, pattern matching is just exact pattern matching. Banana Waffle Monkey says, yo dog, I heard you like functions, right? So we do functions within our functional language, right? Oof. Colgatinotab says, you said you wanted to introduce stuff before you use them, but when we go to let, that does it. You preferred where? No, I mean... Right now, when reading about it, Colgatinotab, yeah. I prefer where when reading about it. Because let, the syntax was foreign to me, Colgatinotab. Yeah, we talked about that yesterday. I preferred where because let was, yeah, foreign, and it still feels arbitrary to me. But I assume that, right, to your point, that when if I practice with let and where, I might get used to let, and it might not be as arbitrary as it feels to me. But it feels like we get to it when we get to it, yeah. This page, more than the other pages, has felt like, yeah, the syntax is something, right? If I'm gonna be doing coding in Haskell, I would have to go to a reference, maybe a better reference than this. This is a tutorial, a guide, a book, right? But a syntax reference to hammer that in. It takes a while for me to learn those things. Melanol the Destroyer says, math time? Bye-bye. Alright, good luck with your maths, Melanol. Right, case is also like an if-else statement, isn't they? Aren't they? I think so, anyway. Right, many imperative languages, C, Java, etc. have case syntax, and if you've ever programmed in them, you probably know what it's about. It is about taking a variable and then executing blocks of code for specific values of the variable, and then maybe including a catch-all block in case the variable has some value for which we didn't set up a case. Haskell takes that concept and one-ups it, okay? Like the name implies, case expressions are, well, expressions. Case expressions are expressions, nice. Much like if-else expressions and the let bindings. Not only can we evaluate expression based on the possible cases of the value of a variable, we can also do pattern matching. Taking a variable, pattern matching it, evaluating pieces of code based on its value. Where have we heard this before? Oh yeah, pattern matching on parameters in function definitions. Well, that's just actually syntactic sugar for case expressions. Oh, these two pieces of code do the same thing and are interchangeable. Okay, so Right, this is our own head function. It takes a list and we return a list of any type, and then we return that type, one of that type. All right, and then if we get an empty list, we throw an error and say there are no, right? There are no heads in the empty list. Otherwise, we will return the head of the list. Yeah, the first item in the list, and we don't care about the rest. Yeah, I remember that. And this one, however, does, right, the same definition up here, the same type. I don't remember what this line was called. Right. And we take the head from a list, right? In case of an empty list, we throw an error and... Oh, so this is a case expression. So all the... when we were talking about doing pattern matchings for each line, this is actually just case. Right, case has been used so much that we don't have to type it out. We use the syntactic sugar. Okay. Colgatina tab says this one doesn't insult the user though. Wait. Oh yeah. Didn't head call the user a dummy in the error? Yes, it did. Yeah. What happened with the insults? I think the functions have been insulting enough recently, so maybe we time to tone it down with the insults. All right, but this we don't use the equal sign here. We use the error. What does the error mean again? Right, if we want to say it in English. Colgatina tab says, I already missed them. The insults? I guess we will find more. Here we go. Excess case, excess of, right. And then we have a, yeah, we have the same syntax. Case excess of, and then we can just go and do however many cases we want to, as long as we keep the same indentation. And we do the catch-all first, and... Probably the best way to do this is the ones that we expect. No, it doesn't matter. We can just do it syntactically, whichever way we want to do it. I'm thinking that... Does it test both of them? Or is it because it's a lazy language it does this? I don't remember. Right, as you can see, the syntax for case expressions is pretty simple. Case expression of pattern and then result. Oh yeah, we just do pattern matching, but why the arrow instead of the equals? Because this here is a function, yeah. We say this function does this. This is no longer a... And more confusing syntax. It only tests until it finds the first that matches. So why don't we put the... Right, I'm just thinking about general ways of doing things. Why don't we take the catch-all at the bottom of the list? Right? Do we really have to make this test every time? Isn't that a waste of resources? Wouldn't it be better to turn these around? Same here, right? that we take the catch-all at the bottom, because why would we evaluate this if we get what we're looking for? Oh, that's because of the, if we do recursion. If we do recursion, we have to do it this way. If we do a recursive call here, we have to have the catch-all before the recursive call. So maybe that's why they do it that way as the norm. But if you don't do recursive calls, then I don't know. We want to do as few tests as possible, right? For optimization reasons. This is the catch-all. Oh, sorry, that's my misunderstanding. I thought that this would be the... All right, this is the exception, right? That was my bad in the language. I meant this, right? This is our result, right? This... did we have another example of a list before? Oh, I don't remember, right? The fat one. Did we do it the same thing? They called it... They didn't call it... They had otherwise, right? Oh, they did do it the way I was thinking. Yeah, they put the otherwise in the end. Yeah, you're right. This is this exception, and this catches all. But this exception doesn't happen very often. That's what I was talking about. Yeah. Usually people will not parse an empty list in here. Or send an empty list into this function. So testing for an empty list every time would be a waste of... Right? Let's say we're gonna call this function 1,000 times, and 2 of those times there will be an empty list. Then making this check 998 times. Well, actually, let's try that. Can we even do this the other way around? I'm not so sure we can. Alright. Oh, shit. I was gonna change them around. So we call head on an empty list. That's gonna... Yeah, wait. Oh yeah, we threw an error. Our error showed up, yeah. No head for empty lists, exactly. Our error did show up, so that's fine. And we... Oh, shit. Yeah, it works fine. Yeah, but that would not work in if you wanted to do recursion. Right, expression is matched against the patterns. Case. Oh yeah. Right, so it doesn't have to be just... Right, it doesn't, this doesn't, we don't, in a case expression, we don't have to do a list or whatever. Case, we can do whatever here. This is an expression, so we could put any expression in here, yeah. Matched against the pattern, yeah. In this, do we have this pattern? Then we get this result. Right, the pattern matching action is the same as expected. The first pattern that matches the expression is used. If it falls through the whole case expression and no suitable pattern is found, a runtime error occurs. Whereas pattern matching on function parameters can only be done when defining functions, case expressions can be used pretty much anywhere. For instance, Colgate says it could work with recursion depending on how you do it. I mean, before, right, what I'm thinking is that, right, if you make, let's say we make a recursive call down, wherever you do a recursive call, on top of that within the function, you have to make it stop somewhere, right? You have to make it stop somewhere. Otherwise you have something infinite on your hand. Yeah, you need to make sure that it stops. If you put x:xs first, you don't have to specify the list for the latter condition. You can use... Alright, I don't know. Where are we talking? Are we talking about this? I mean, this function wouldn't, like... There's no reason of doing... recursively asking for the... I mean, I suppose we could do. I remember us doing that, but that's out of scope. That's not... yeah. Where we don't care about the underscore instead of the list. Sure. Oops. Alright. Describe list, alright. The list is... wait. Empty. A singleton list. A longer list. Is this Song of Storms? Rock Forest? Not Song of Storms. That function, no recursion, just a syntax thing. Oh, yeah. I kind of like the... I kind of like this. Yeah. It's more clear, right? It's an empty list. It's an empty list. We can do stuff like this with an empty list. Right. Plus, and then we call case for the list of... All right. In case the list is empty, then we call it an empty string, and we call it a singleton list if it's a singleton list, and we call it a longer list. This makes sense, yeah. But we could do this... Right. We wouldn't want to do pattern matching if we wanted to do this, because we would have to we had to repeat ourselves. The list is, we would have to repeat this over and over and over again if we just did normal pattern matching instead in case off. So wouldn't it be best to always use the case off syntax instead of doing the pattern matching? I like to do the same thing, right? I don't know. This feels like the thing to learn rather than the pattern matching. They are useful for pattern matching against something in the middle of an expression, because pattern matching in function definitions is syntactic sugar for case expressions. We could have also defined it like so. Oh no, we can do it. Oh yeah, with where. There are too many choices. I don't like the choices. I just want one way to do things and then do it that way. One way of doing it and do it that way. Because my mind goes to, well, if I can do it like this and I can do it like this, what should I be doing as a noob, right? I understand that when you get better, you're happy about the choices, but right now as a noob, I don't want to see this. I want you to tell me just do it this way. Right. Colgate on tab says pattern matching is for case what yeah, exactly. Syntactic sugar, right? That's I don't like it. Personally. Because it's just confusing. I'm bad at remembering these things. Like I won't remember these things. So therefore I would want as little syntactic sugar as possible, or only the syntactic sugar, and then, right? This could be added way later when it's necessary. Or actually I would stay away from it as a noob completely, because that's, for me, like my personal type of learning, right? It's a taste thing, definitely. But I assume that this might be a good reference to go back to, maybe. The syntax and functions, maybe. Right, it's confusing enough to do something one way, and then we have to do it another way as well. That was right, exactly. Like we had the list, the two different ways of writing lists. I had the same complaint there, right? Why do I have to learn both of these right now? Can't we just learn one of them to start out? Yeah. Colgate tab says that case can be used as an expression, so if you only intend to use one, use cases. Right, but that's not up to me. I'm gonna use whatever the guide is gonna tell me to, right? We're gonna end up with another function here. Oh, look here. Here they use guards and where syntax. And here they use pattern matching syntax. And guards again. Guards and pattern matching. But they don't use the case thing. So therefore I'm not going to use the case thing. Therefore, talking about the case before, oh, here is let though. We started using let. It's more a criticism against the book rather than what I want to do. Well, Getino tab says I don't use case much either. Yeah, it's more typing. Yeah, I mean that's why they didn't do it, because it's more typing, I guess. That's why they do syntactic sugar, because it's less typing. They build the language to function in a certain way, and then they make shortcuts. And I get why they do shortcuts. It's just, I don't know. Let's keep going. Let's learn about recursion. Hello, recursion. Every time I see one of these, babushka doll, right? I think of another Tim Minchin song. Yeah. Not Perfect, I think it's called. Great song. Interestingly, my two favorite songs of Tim Minchin. Right, if I just want to listen to music, I really like those two songs. If I want to have watch a show, I just watch one of the shows because the shows are more like stand-up comedy. And usually stand-up comedy you don't listen to over and over, like a song you can listen to over and over. Right. We mentioned recursion briefly in the previous chapter. In this chapter, we'll take a closer look at recursion, why it's important to Haskell, and how we can work out very concise and elegant solutions to problems by thinking recursively. That's something that I want to learn, thinking recursively. I like this. If you still don't know what recursion is, read this sentence. Just kidding. Right. I get the joke, yeah. Read the sentence. Okay, if you still don't know what recursion is, read the sentence. Okay, we will read the sentence. If you still don't know what I mean, we won't get anywhere, but recursion is actually a way of defining functions in which the function is applied inside its own definition. Yep. Definitions in mathematics are often given recursively. For instance, the Fibonacci sequence is defined recursively. First, we define the first two Fibonacci numbers non-recursively. We say that f for 0 is 0 and the function for 1 is 1, meaning that the 0ths in the first Fibonacci numbers are 0 and 1 respectively. Then we say that for any other natural number, that Fibonacci number is the sum of the previous two Fibonacci numbers. So fn is equal to fn minus 1 plus fn minus 2. Oh, yeah. I got confused first. But yeah, we take the previous number and and the number before that. Yeah, the sum of the two previous numbers. That way, f3 is f2 plus f1, yeah? Which is f1 plus f0 plus f1. Okay, yeah. Because now we've come down to only non-recursively defined Fibonacci numbers. We can say that f3 is 2. Having an element or two in a recursion, in a recursion definition, defined non-recursively. Oh man, are you kidding me? I'll completely lost track of this sentence. All right. Having an element or two in a recursion definition, defined non-recursively. Fuck you, dude. I don't understand, right? We're doing maths. Fucking maths. All right, like f0 and f1 here is also called the edge conditions. All right, that's what I was talking about earlier when I called it the catch-all. But those were the edge conditions, was what I was thinking about in the catch-alls. And it is important if you want your recursive function to terminate. Yeah. If we hadn't defined f0 and f1 non-recursively, you'd never get a solution. Never get a solution, any number, because you'd reach 0 and then you go into negative numbers. All of a sudden, you'd be saying that f minus 2000 is f minus 2001 plus f minus 2002, and there still wouldn't be an end in sight. Yeah, exactly. You need edge conditions in a recursion. What did I call them? Catch-alls. I meant edge conditions. Recursion is important to Haskell because unlike imperative languages, you do computations in Haskell by declaring what something is instead of declaring how you get it. Yeah. This song needs to be skipped because it's a little bit... It takes my focus away. This is Final Fantasy VII, right? Yeah. That's why there are no... Wait. Yeah, that's why there are no while loops or for loops in Haskell, and instead, many times we have to use recursion to declare what something is. Yeah, because when you do a while loop or for loop explicitly, then you're telling the computer what to do. You don't define what something is. That's the whole point of functional programming. Yep. Maximum, awesome. The maximum function takes a list of things that can be ordered. For example, instances of the order type class. Wait. I always forget. No, IE is, for example, EG is that is. Yeah, that is instances of the order type class and returns the biggest of them. Think about how you'd implement that in an imperative fashion. Right. Yeah, that's implementing that. Well, we would kind of do it the same way, because in Python, for example, there is a function, like there's a built-in where you can do that, I'm pretty sure. But if you want to implement it yourself in an imperative fashion, you would have to... I would probably just take the list, take the first number, compare it to the second number, and discard the lower of the two, and then just keep on doing that. You'd probably set up a variable to hold the maximum value so far, yeah. And then you loop through the elements of a list, and if the element is bigger than the current maximum value, you'd replace that with the element. Yeah, exactly. Yeah, you would set up a variable indeed. That is what you would have to do. Right, the maximum value that remains at the end is the result. Phew, that's quite a lot of words to describe such a simple algorithm. Is it a simple algorithm? Now it kind of feels like, well, that's if you want to do it in C and have to set it up yourself. But, right, in Python we wouldn't do that. In Python we would just... I'm pretty sure there is a function, a built-in function or whatever, where you could just order the list. And it feels like that is exactly what we're doing in Haskell. We just take one of the built-in functions and order the list. Maybe not. Now let's see how we define it recursively. Right, we're gonna define it recursively. We're not gonna call a function, we'll do it ourselves. We could first set up an edge condition and say that the maximum of a singleton list is equal to the only element in it. That makes sense. Then we can say that the maximum of a longer list is the head if the head is bigger than the maximum of the tail. If the maximum of the tail is bigger, well, then it's the maximum of the tail. That's it. Now let's implement it in Haskell. All right. Right, we take a list of ord class types. Class types? Yeah. Type class? Yeah. Right. We can't get the maximum of an empty list is, well... No, yeah, I would throw an error. I was thinking that we could return 0, but that's not real. That doesn't really work. We have not a number. We have none. Not 0, so 0 wouldn't work. Right, and definitely, right, if we said 0, that would also be broken because we use negative numbers here. We haven't been using negative numbers, so that wouldn't work. Right. Alright, and if we have a singleton list, then that is the biggest, yeah. Get tab says you could put the empty list last here, for example, and... Oh yeah, you could. With the recursive stuff, right? Yeah, we could put both of these. Because an empty list would fail here, right? And the singleton list would fail here. So it would just move down. So you could put the recursion on top. Actually, not the X one. Yeah, not this one probably. Let's see. Let's see how it's done, by the way. Alright, we take... It's a guard thing. So we do comparisons. That we compare X. Right, this is... Wait. MaxTail? Oh, right. That's the helper. I was just wondering, what is that? Right. It's the helper function. Alright. We check if X is bigger than the max of the tail, then X. Otherwise, we take the max of the tail. Right, and the max of the tail is... is the maximum of XS. Right, because we call the tail. No. Yeah, here it is. Yeah, it is the tail. Man. This syntax. This is how you do it recursively. I need to just look at it for a while, eh? Boolean on tap says... Yeah, singleton list is X into a list. So if you define it as X into Y into XS, and then said MaxTail is maximum. I mean, I still don't get this. Do we have to change it around when I don't get the normal? I'm just gonna skip what you read there because I don't quite get this. So let's not change it. Let's just take it what they wrote and not change it around. Right, we're learning about recursion here. Trying to learn about recursion here. But these two, this we've already learned, right? This is just, right. We return an error if we get an empty list, and this one is super easy, right? If there's only one element in the list, then that is the biggest one, and the smallest one, and the only one. Right, and here, this here is the X is the head of the list, and XS is the tail of the list. So, if X is bigger than the max tail, then we return X, and then we're done. Yeah, that's it. We're done with the function. Right, but we have to call MaxTail, and that's where the recursion happens, because MaxTail calls maximum again, and that's how we think with recursion. Oh man. Wrapping my head around this is annoying. Why do we have to think in recursions? Because we define what things are, not how to do them. It's rough. Right. So the MaxTail, right? That's what we call... What's that? I think I have like a fly or a mosquito in here. I think it's time for them to die. Alright. The good thing is no side effects. That's always when we say they... Yeah. No side effects. Right, but when we have done this recursively, right, when we call this recursively, we do get the MaxTail. Because we call this for however long the list is, right? We would still, like, under the hood, it still loops through. It does the same thing, right? The machine code is the same. What happens in the machine is... Where is it? Yeah. That's what we're doing, right? We are doing the same thing, right? We're setting up the variable. This is it. And we test it to all the others. And then we iterate recursively through the list. That is what is happening. Right, as you can see, pattern matching goes great with recursion. Most imperative languages don't have a pattern matching, so you have to make a lot of if-else statements to test for edge conditions. Here we simply put them out as pattern. So the first edge condition says that if the list is empty, crash. Makes sense because what's the maximum of an empty list? I don't know. The second pattern also lays out an edge condition. It says that if it is a singleton list, just give them back the only element. Yeah. Now the third pattern is where the action happens. We use pattern matching to split a list into a head and a tail. This is a very common idiom when doing recursion with lists, so get used to it. Okay. Which is exactly the same thing we do in imperative languages. Right. We use a where binding to define MaxTail as the maximum of the rest of the list. Then we check if the head is greater than the maximum of the rest of the list. If it is, then we return the head. Otherwise, we return the maximum of the rest of the list. Let's take an example list of numbers and check out how this would work on them. 251. Right. We call maximum on that. The first two patterns won't match. Yep. The third one will, and the list is split into 2 and 51. Exactly. That is what happens here. 2, a list of 51. The where clause wants to know the maximum of 51. So we follow that route. Right. Yeah, exactly. It splits them out into 5 and 1. Again, the where clause wants to know the maximum of 1. Because it's the edge condition, it returns 1, finally. So going up one step, comparing 5 to the maximum of 1, which is 1, we obviously get back 5. So now we know the maximum of 5 and 1. We go up one step again. And where we had 2 and 5 and 1, comparing 2 to 5, and then we choose 5. An even clearer way of writing this function is to use max. If you remember, max is a function that takes two numbers and returns the bigger of them. Here's how we could rewrite maximum by using max. Right. Throw the error, we do the thing, and then we just use the function where we take the max out of. Oh, max just takes two numbers. Yeah, it doesn't take a list. How's that for elegant? In essence, the maximum of a list is the max of the first element and the maximum of the tail. The maximum of the list is the max of the first element and the maximum of the tail. Yeah. max between x and the maximum of tail. Man, my mind keep going to what is happening in the computer, right? What does the compiler do? I don't know. Right. Oh, and this is the whole thing. The picture didn't. Yeah. Definitely a language for mathematicians, eh? Haskell. Because this here is probably easy for someone who's a mathematician to just see immediately what's going on. For me, this is a mess. I can figure it out, right? We're doing it's this exact same thing. It's just defined recursively. Right? It's easier for me to wrap my head around, right? Instead saying just, oh, first we check the 2, and then we check the 5, and then we check the 1. That's when you do a loop. You just loop over. You have the list, and then you just, first we check here, then we check here, and then we check here. Few more recursive functions. Alright. Now that we know how to generally think recursively, oh, I don't know that. Oof. Let's implement a few functions using recursions. Right, first off, we'll implement replicate. Right, replicate takes an int and some element and returns a list that has several repetitions of the same element. For instance, replicate 5,3 returns 555. Yeah, replicate 5. It replicate 3 times 5. Ooh. I would put these on the other way around. Yeah. No, I wouldn't. Sorry, it's 3x. Yeah, 3, 5. No, it makes sense that way. In my mind, I was just thinking, yeah, 3, 5 times. But that's not what we're doing with saying 3 5s. That's what we get. Alright, let's think about the edge condition. My guess is that the edge condition is 0 or less. If we try to replicate something 0 times, it should return an empty list. Also for negative numbers, because it doesn't really make sense. Yeah, return... that doesn't make sense. Yeah, so if n is smaller or equal to 0, then we return the empty list. Otherwise, we recursively call it again. In my mind, it kind of feels like thinking with loops or thinking recursively is just... it's the same, right? It's thinking with loops. This is every time we loop over, right? This is where we stop. This is where we stop, and then we just go down the list. I guess in this example, usually what you do is, in imperative languages, you start at 0, right? 0 index, 1 index, 2 index, 3 index, until you reach the maximum, right? But in here, you define it the other way around, right? You go from the top and go down. You could do that, I suppose, easily in imperative languages as well, but it's usually not the way to do it. It doesn't really matter. Well, in functional languages, it makes sense to do it this way. Otherwise, we would have to define right? Because if, let's say we did it x times, right? If n was bigger than 5, then we can't return an empty list. No, we have to do it this way, right? To do it recursively. All right. Let's do this. Let's check here, right? You take something that has to be a number and be able to reorder it, yeah. And we take I and to any type and then a list of that type. Wait, why is there an A here? Oh, right. We need a number for how many times to do it, but we can replicate. It doesn't matter. We don't have to replicate a 5. We can replicate a character or a word or a string or whatever. Yeah. I get it. That's why it says A here. A can be anything because we can put anything in a list. Colgate tab says we could put them the other way around if you want to reduce the amount of checks. No, we have to stop, right? We have to put this. Yeah. If we want this to work for a list that is, I don't know, 1,000 items long, right? If we want to put n as 1,000, we don't know. N should be able to be anything, so we have to go from n and go down, right? I mean, we could start at 0 and go up, right? N plus 1. Man. I feel my brain isn't working today. Right, if n is bigger than 0, then x, replicate n plus 1 is x. Yeah, it becomes the same, otherwise the empty list. Right, n is smaller than. No, wait. But when you do that, what happens when you reach n is bigger than 0? Yeah, as soon as you go n minus 1, you have to go down. Yeah, so you cannot count up, you have to count down. Yeah. To hit the edge condition. You don't want an upper edge condition. Because you don't want to change variables around. That's what you do in imperative language. That's the side effect thing, right? Where you can decide, you can go up to n and stop at n. But that creates, like you said, right? We create a, where was it? Yeah, you'd set up a variable. And that variable is arbitrary and changeable. That variable is created when the function is called. Oh, you're still talking about the other thing. Right. That you could flip these two, you could flip the places of these two. Right, you don't have to check for the edge condition all the time. Yeah, you don't have to. In this loop, right, this recursive loop would check for the edge condition every time. Right, that's what you did. You flipped them around. Yeah, you put otherwise an empty list down here. Yeah. I get that. That would be more efficient, like we talked about before. Indeed. Colgatinotab says, or I guess as just otherwise there's not really an extra check. Yeah, I wonder why he doesn't do it that way. Now that you mention it, right? Because we tried this before, right? We tried it before and it works just fine. Just like it would. Oh. It would work fine to check if n is greater than 0. Then we would do the x replicate -1 x. It's just the same thing, right? Yeah. And here we return otherwise. We return the empty list. Does that work? Let's try it. Instead of understanding, we just science it. Yeah, right. So replicate. All right. 42 10 times. No, it's the other way around. Shit, I forget again. 10 42s. Yeah. And it works just fine. And if we do it 0 times, we just return. Yeah, we have it 0 times. It's got to be more efficient. Right, we used, but right, it doesn't matter. We use guards here instead of patterns because we're testing for a Boolean condition. Well, it does matter, but you know what I mean. It's not what we're talking about right now. Right now, we're trying to learn about how the recursive function works and wrap my head around them. Because in my mind, I don't think with recursions. I just think in loops. That's what I see. I just see loops. I don't see recursions. I don't see this. I see a loop. I see a loop that goes around and around. Right, we use guards instead of patterns because we're testing for a Boolean condition. Indeed. If n is less than or equal to 0, return an empty list. Yeah. Otherwise, return a list that has x as the first element and then x replicated n-1 times as the tail. Eventually, the n-1 part will cause our function to reach the edge condition. Exactly. Olgetinotab says, I think this book is a more noob-friendly way. Maybe it is. I mean, I'm a noob. I don't know. Note that num is not a subclass of ord. No, we have just I is part of num's type class and ord type class. And that means what constitutes for a number doesn't really have to adhere to an ordering. So that's why we have to specify both the num and ord class constraints when doing addition or subtraction and also comparisons. Right. I think, yeah, it's lunchtime, so we'll continue with the take instead of replicate and call it there. Call it there and continue tomorrow.